Assalamualaikum and a very good day. This is a part of BMFG 1213 Engineering Materials, and this particular lecture will cover Chapter 7, Characteristics, Processing and Applications of Metal and Alloys, okay, including phase diagram. So before we move on further into the chapter, so let's have a look at the course learning outcomes. So as we already know, this subject has the three learning outcomes, okay? And this particular chapter will cover the second outcomes, okay, which is to analyze the properties of engineering materials based on its structure. So listed here are the learning outcomes that we are going to cover. The first one is to differentiate metal and alloy. And the second one is to describe the basic concept of phase diagram. Next is to describe the binary phase diagram. And then it follows with the discussion and interpretation of a phase diagram. And lastly, we're going to look at how to describe the iron-carbon system. So my lecture will be divided into few parts. The first part will cover the classification of metal and alloys, and the second part will be talking about the basic concepts of phase diagram, a binary phase diagram, and also the interpretation of phase diagram. And the last part is going to be on the iron-carbon system, whereby we're going to look at the iron and iron carbide phase diagram, okay, which is very important for steel industry. So next, here, okay, we are asked, okay, about what are metals, okay. So before you can actually answer these questions, okay, so let's go back to chapter 1, okay. So in chapter 1, you have actually do the classification of materials in general, okay. So let me just, okay, so materials can be classified into few categories, okay, from chapter 1. All right, so we have metals, we also have ceramics, we have polymer, and we also have composite. Okay, so this is the basic classification of materials, okay. So before you can answer what are metals, okay, in order to answer this question, okay, you need to know, okay, what are the characteristics of metals and what make it differs from the other materials. All right, so metals in general, okay, if you are looking at the physical appearance or the physical properties of the metals, okay, so normally it's shinier, it's shiny, all right, and it's also normally heavier and also harder than the other groups of materials, right? And on top of that, okay, metals are also good conductors, okay, of heat, both heat and electricity, okay. And then metals also have good malleability, okay. That means, okay, it can be shaped or bent, okay, without breaking, so that, okay, it has a good formability, it can be formed into shapes, right? And metals also have good ductility. All right, so this is the characteristics, okay, of metals in general, right? So the examples of metals, okay, that we can list out maybe a few of them, okay. So the most common one might probably be iron, right? Fe, ferrum. All right, and then we have aluminium, okay. We also have copper, Cu. We have titanium, Ti. We have nickel, magnesium, and so on. Alright, so this is just a few example of metals, okay, which is abundantly existed, okay, in nature. Alright. Okay, now let's have a look at the next slide, okay, is on the metallic bonding for pure metals, okay. So let me just, alright, so from chapter 2, okay, in chapter 2, alright, in chapter 2, okay, we already learned about the few types of primary bonding, okay. So the bonding between the atoms, okay, in metals, alright, it actually comes from the metallic bonding, okay. So in metallic bonding, okay, we know or we already learned about the bonding between atoms and how these pure metal atoms are bonded together, okay, by the metallic bonding. All right, so let's say we have here the atoms, okay. So just for argument's sake, let's say it's iron or ferrum. All right, so with the nucleus of each of these atoms, okay, being in the crystal structure, okay, we also have the free electrons. All right, so these free electrons, okay, which is negatively charged, okay, will actually form what we call as the sea of electrons. All right, so the sea of electrons, okay, is what that kept the atoms together, okay. So it keep the atoms together, right? So because of that, okay, the bonding, okay, between atoms, okay, in metals, okay, are very strong. It means you need, okay, a very good force, okay, in order to separate the atoms. All right, and in chapter 2, okay, we also have look at how this bonding is actually affecting the properties of the metals, okay. For example, okay, if we are still looking at the atoms arrangement here, okay, for iron, all right, so let's say we apply certain force of load, okay, so we apply force here. All right, so because of the force, okay, it actually deform, right? So the force is actually strong enough to cause deformation, right? Means, okay, some of the atoms, okay, will be relocated from its original position. All right, so now, all right, since the deformation already occurs, okay, so, but because of the sea of electrons, okay, so it can still like bind all the atoms together, okay. It's not going to break instantaneously, okay, as opposed to the ionic bonding, okay, which normally seen in ceramic materials, okay. For ceramic materials, also let's just draw this, okay. So for ceramic materials, okay, since it's a bonding between non-metal and metals, okay, so you know, okay, in ionic bonding, okay, we have like charges, okay, and these charges, okay, of anion and cation, okay, is going to sit next to each other, okay, within the crystal structure. So let's just quickly do this. So let's this represent the charges, okay, of the ions, okay, which is located next to each other. So it's always the opposite charge, okay, which is sitting to the other charge, okay, to keep the equilibrium. All right, so let's say now, okay, for the same materials, okay, we are applying like certain kind of force. All right, and this force, okay, is strong enough to cause deformation, okay, to the structure. So let's just quickly draw this. Now let's see, the first time, okay, at equilibrium, okay, so we have all the opposite charges, okay, sitting next to each other, right? But once the deformation takes place, okay, so let me just draw this, okay, so this might happen. All right, so as you can see here now, right, we have like the same charges of ions sitting next to each other, and we know the same charge will repels. Okay, so if the repulsion is actually occurs, okay, at few planes, okay, within the crystal structure, so it will repels, okay, instantaneously, and this will cause the ceramic materials, okay, to break in brittle manner, okay, as opposed to the metallic bonding just now. All right, so since, okay, what holds the atoms together are the sea of electrons, okay, so as long as the overlapping of atoms with its sea of electron, okay, is actually strong enough or big enough, okay, to bear the force or the load, okay, which is being applied to it, okay, so it will stay intact, okay, even though deformation has occurred. Okay, so this is what, okay, that has been observed, okay, by the necking condition. Okay, so remember in the previous chapter, okay, we have learned about the mechanical properties of metals. Okay, so when we are pulling the metals in tension in tensile test, okay, so normally, okay, we will observe the necking, okay, at the center of the gauge length, okay, before it actually fracture into two parts. All right, why? Okay, because of this sea of electrons, okay, which is actually pulling the atoms together. All right, so until it's actually not strong, it's actually can no longer bear the load, okay, then only it will fracture into two parts. All right, so this is the comparison, okay, on how the atomic bonding, okay, between metals and other material, okay, such as ceramic, okay, differs from each other, and how it actually affecting the properties of the materials. Okay, now this slide is actually asking you what are alloys, right? So during the previous slides, okay, we already look at the general description of metals, okay, and now, okay, we are coming to alloys. All right, so alloys by definition, okay, is a mixture of two or more elements in solid solution in which the major component is a metal. All right, so I think if you're asked to name one type of alloy that you are very familiar with, okay, I'm sure most of you will come out with steel, right? Okay, so now in order to describe, okay, the theory behind the or the concepts of alloys, okay, so let me just draw something for you. Okay, all right, to start on the concepts of alloys, okay, let's have a look at the atomic arrangement for metals. All right, so this is the atomic arrangement for metals, okay, and we have like the bonding, okay, between each of the atoms. All right, so let's say, okay, we're taking this as a perfect crystal of iron, Fe. Right, so this is what we have learned in chapter 3. Okay, we have learned about the arrangement of atom for crystalline materials, and based on what we have learned in chapter 3, okay, all the atoms, okay, will be on its lattice side, okay, where it should be, right? So it's a perfect crystal, okay, at that point. All right, but then as we advance into chapter 4, okay, where we are looking at the imperfection in solids, okay, we know that such thing as a perfect crystal doesn't exist. All right, so what is actually there, okay, within the crystal structure? Okay, so if I can draw it for you, okay, so after we have learned chapter 4, right, this is a more realistic, okay, representation of the atoms, okay, within the crystal structure. All right, so what we have here is, okay, we have an imperfections, okay, in the form of vacancy. All right, so we have a vacancy here. So we all know, okay, vacancy is where one atom is missing from its lattice side. Right, so this is a more realistic representation of the atomic structure. Okay, let's say this is for iron. All right, so because of the imperfection, okay, so such as vacancy, which occur within the crystal structure, okay, so whenever we apply, okay, load, okay, or force, okay, onto the materials, okay, so if the force is high enough, okay, so that it can actually surpass the energy barrier, okay, so one of these atoms can actually move and fill in the voids or the vacancy. All right, and leaving its lattice side vacant. All right, and if we keep on continuous supplying the force, okay, so other atoms, okay, from the vicinity will eventually fill in the new gap, okay, and so on. All right, so because of this, okay, movements of atoms within the crystal structure, okay, it will somehow reduce, okay, the strength of the iron. Okay, so the strength is actually reduced, okay, or decreased. All right, so now, okay, for most of the engineering applications, okay, so they would require the usage of a good of a material, okay, especially metals, okay, with good strength. All right, and in this case, because of the imperfection which occurs in the crystal structure of iron, okay, so the strength of the iron, okay, is actually lower, okay, than the theoretical value. All right, so what we can do, okay, in order to improve the strength, okay, so if we want to improve the strength of the iron, okay, we need to add something else. Okay, so we can add, okay, what we call as the alloying element. Okay, an alloying element, okay, is actually added to metals, okay, for different function and different purposes. Okay, so in order to cater with the strength of the iron, okay, so what we add, okay, as an alloying element is the carbon. All right, so we add carbon, okay, into the interstitial side of the iron so that it becomes steel. All right, so in this case, let me draw it for you. Right, so let's say the red colored circle is for the atoms for iron, and then, okay, we're going to add carbon, okay, somewhere in the interstitial side of the iron. Okay, so this is carbon. All right, again, okay, if you look at this phenomena of carbon into iron, okay, this is also another representative of the imperfection in solids. Because why? Okay, in at this point, okay, carbon is actually, okay, impurities, okay, within the iron atoms. All right, but then, okay, for this particular case, all right, the carbon is intentionally added, all right. So it's an intentionally added impurities, okay, because we have learned in chapter 4, okay, imperfection, okay, might occur unintentionally, okay, during the processing or the solidification process, but it can also be intentionally added. Okay, so this is an example of how impurities can be intentionally added in order to improve certain properties of materials. Okay, certain properties of materials, okay, or metals. Okay, so now, okay, since, okay, we already have the carbon, okay, in the interstitial site of iron, okay, it becomes, okay, what we call as steam. Alright, so there are many other alloying elements that we can add into metals, okay, in order to alter or improve, okay, certain properties, okay, such as the maybe the conductivity. Okay, so conductivity normally we'll add silver, okay, or some of the alloying element, okay, is added, okay, to the host atoms, okay, to improve the corrosion resistance maybe, okay, and okay, so there are a lot more alloying element, okay, that can be added, okay, in small percentage, okay, to metals, okay, in order to improve, okay, certain properties of the metals. All right, so this is the basic concept of alloy. All right, so let's just go back to the slide. All right, so now here it says that metal can be deformed. Okay, so the examples of metal used for alloys, okay, are lead, platinum, zinc, nickel, okay, and deformation, okay, that occurs through work hardening, okay, which is the strengthening metal, okay, by plastic deformation. Okay, so deformation can occur via work hardening, okay, which is the strengthening metal by plastic deformation. All right, okay, now here, okay, it says that alloys, okay, is stronger than pure metal. Okay, so the presence of the other atoms, okay, smaller or bigger, it disrupt the symmetry of the layers, okay, and it reduce the slip ability of one layer next to another. All right, as being represented by the figure 1.5 here. All right, so let's say, okay, this is the how it looks like. All right, I'm sorry, let me just, so this is how it looks like, okay, the atoms, okay, within the crystal structure. All right, so without the presence of alloys, okay, so if we apply force, okay, it will easily slide, okay, through the planes, okay, causing the deformation to take place, okay, deformation. All right, but okay, if we have, okay, the alloying elements, okay, in between the host atoms, okay, once we applied force, okay, the force, okay, will try to go through the plane, okay, of reference, okay, but then, okay, once it actually come across the alloying element, so this is the alloying element, okay, so it's either stop or it's going to be slowed down. Okay, why? Because in order to actually cross through the alloying elements, okay, it need another set of need to surpass another set of energy barrier. All right, because it's a different element. Okay, so it has a different strength, okay, within the atoms. Okay, so if you want to go through and pass through it, okay, so you need to put extra effort. All right, so if the force, okay, is not strong enough, okay, it will stop completely. Okay, once it's actually bump onto the alloying element. All right, but if the force is actually be able to surpass the energy barrier of the alloying element, okay, it will pass through, but still, okay, it will slow down the process of the deformation. Right, so it will still improve, okay, let's say the strength of the materials, okay, even though it cannot stop the force from stop the deformation from occurs completely, but it can slow it down. All right, so that's the purpose of the alloying element. Okay, so that's why it says here, okay, alloys are stronger than pure metals. All right, so alloys in pure metal, okay, can either be substitutional, right, or it can also be the interstitial alloy. All right, so for interstitial alloy, normally, okay, the requirement is that the alloying element radius, okay, is much smaller than the host atoms. Okay, next is the classification of metals and metal alloys. All right, okay, metals and metal alloys, okay, can be classified by several categories. Okay, the most common one is by the iron content. All right, so if we are looking at the classification of metals and metal alloys based on its iron content, okay, so we can put it into two groups. The first one is ferrous metal and its alloy, and the second one is the non-ferrous metal and its alloy. All right, so as the name implies, when a metal contains iron, okay, it is known as ferrous metal. Okay, so the iron actually imparts magnetic properties to the material and makes them prone to corrosion. Okay, so metals that do not have any iron content are non-ferrous metals. So these metals do not possess any magnetic properties. For example, non-ferrous metals and metal alloy, okay, include but not limited to aluminium, lead, brass, copper, and zinc. Okay, so if we are looking at the ferrous metals and alloys, okay, it can be subdivided into two groups. Okay, the first one is what we call as steels, and the second one is what we call as the cast iron. All right, so the difference, okay, between steels and cast iron lies in the percentage of carbon, right, within the steel. Okay, so steel, okay, normally contain, okay, the lower amount or lower percentage of carbon, okay, less than 1.4 weight percent, and from 3 to 4.5 weight percent carbon, okay, it falls under the category of cast iron. All right, and for steel, okay, it can further be subdivided into low carbon steel, okay, for example, medium carbon steel, okay, high carbon steel, okay, and we also have like tool steel, okay, which have a higher amount of carbon percentage. All right, okay, so we're going to look more onto this. Okay, so this is what we call the iron and iron carbide phase diagram. Iron and iron carbide phase diagram. Okay, so we'll look more onto this, okay, on the third part, okay, of my lecture. All right, so so this is the first way to classify metal and metal alloys, okay, which is by the iron content. All right, but then metals, okay, and metal alloys can also be classified based on their atomic structure. okay, according to the periodic table, right? So you can always go and check the periodic table, okay? So when metals are characterized based on the atomic structure, they are known as alkaline earth, or a transition metal, right? So you can look out the periodic table that shows you where they are located within the periodic table, and you can figure out what are the metals that fall into the same group. So metals belongs to the same group behave similarly when reacting with other elements. Okay, thus they have similar chemical properties. For example, if you look at the periodic table, okay, the alkali metals are so reactive, okay, that they are generally found in nature combined with other elements. Okay, so if you look at the first column of group, okay, on your left hand side, okay, of the periodic table, okay, so that is the column for group 1. So all the 6 elements in group 1 except for hydrogen falls into this category. Okay, so it's actually considered as alkali metals. All right, so that's the second way to classify metals. Okay, first by the ion content, okay, so it's ferrous or non-ferrous, and the second one is by the atomic structure. Okay, so you have to refer to the periodic table. And another way to differentiate metal is by looking at their interactions with magnets, okay, which is the magnetism of the metals. Right, so there are 3 ways in which material can respond to magnetic field. Okay, we have ferromagnetic material, paramagnetic materials, and dimagnetic materials. Okay, so briefly, okay, ferromagnetic metals can be magnetized when it is induced by sufficient magnetic field. And on the other hand, paramagnetic metals can be magnetized, but it will lose its magnetism once the magnetic field is taken away, and it only shows weak interactions with magnets. Okay, and lastly, there is a group called dimagnetic metals that rather show a very weak or no interactions at all with magnets. Okay, so those are the 3 ways, okay, in which we can categorize metals and metals alloys. Okay, but the most commonly used, okay, the first one, okay, which is based on its iron content. All right, okay, so I guess that's the end of part 1, okay, with the very brief introduction, okay, on metal and metal alloys. All right, so I'll continue on my lecture, okay, with the second part, okay, when we are going to look at the phase diagram. So yeah, all right, so I think that's it for the first part. Thank you so much for your attention. I'll see you in the second part, inshallah.